Welcome back, everyone. So I'm very excited to continue with the last part of our workshop today. I'm very delighted to introduce our next speaker, which is Dr. Sahil Gulati, who received his PhD in pharmacology and structural biology at Case Western University, and later on did his postdoc at University of California, Irvine. As of now, Sahil is the applications manager of life sciences at Gatan and spearheads business development of life science products and develops improved methods for cryo-electron microscopy. And today, Sahil will talk to us about software that can automate and streamline microelectron diffraction experiments. So Sahil, it's a pleasure. The virtual floor is yours.
Thank you for the introduction, Paul. I'm going to be sharing my screen. All right, hopefully you can see my screen.
Yes, we can see it. Thanks.
Perfect. All right, good afternoon, everyone. My name is Sahil Gulati. As Paul indicated already, I'm the applications manager of life sciences at Abbott at Gatan. And today I have been given a pleasure to speak to you all about Latitude D software, which is the automated software solution from Gatan for micro-LED data collection. Now, before going and digging on to Latitude D in particular, I will just briefly mention that Latitude offers all flavors of imaging and diffraction automated data collection softwares, including Latitude S for single particle, Latitude T for tomography data acquisition, and Latitude D for diffraction micro-LED data collection. Now, focusing on Latitude D today, Latitude D delivers the automation and high throughput for micro-LED data collection. There are several features you'll find very beneficial for Latitude D, including its unrivaled productivity with Gatan cameras, because since the software and the hardware, the cameras that you use are produced by the same company, you can imagine a very good seamless integration between both, and therefore the productivity that you get is high as well. Secondly, Latitude D offers automation and decreases manual user intervention there, which enables you to screen your crystals along with doing data collection on the crystals. So you don't have to collect data on every crystal that you find. You can screen the crystals, making sure the crystal that you are imaging is the quality that you actually want. And if you like it, you can do the tomography electron diffraction data collection. Thirdly, it provides extensive task and session tracking. It gives you the opportunity to know how much time is left for your data collection. So that you can decide that you have 10 minutes for grabbing coffee with your friend, so that you do not create issues within your friendship. You know when to go home, you know when to come back. And finally, it offers user-friendly workflow, offering zero downtime and immediate productivity. That means the moment it has been set up for you by a Gatan engineer, you can use the software to the next day, having a zero downtime. You don't have to spend months and months knowing the software, getting to know how it's supposed to be used, and it's very user-friendly to use. Speaking about the Gatan cameras that are compatible with Latitude D, Latitude D is compatible with almost all the latest cameras offered by Gatan, including the Stella camera, the K3 camera, and both of them, you have them already, the K2 camera, OneView, and Rio, and all the GIF versions of these cameras. There are a few more features that Latitude D offers, and these are the things that I mentioned briefly before, that you have the ability to screen your crystals, make sure there is no crystal mosaicity there, if the crystal is not twinned, and the diffraction quality that you anticipate is what you're getting from that crystal. And following from there, you can decide whether you would like to collect a full tail series on that crystal or not. And finally, you have the opportunity to do automatic mechanical use-centric height adjustment on every crystal, because you would like to make sure that once you target a crystal and you tilt the stage, the crystal remains in the field of view, so that the diffraction quality of the tail series that you get is at par and exactly what you want at the end of the day. With this short introduction, I will be quickly going through Latitude D demo, where we'll be discussing about how to set up microscope states for micro ED data collection, what is the general workflow of Latitude D, and some mock data collection. But before I go there, I'll just briefly mention it's a simulated demo. That means there is no microscope on the other end. So this gives us an opportunity to smoothly sail through the workflow of Latitude D. Now, while I'm setting up the demo, if you have any questions about the software or about the cameras, feel free to ask. All right, hopefully you can see the screen that I'm trying to display, which you should see Gatan Microscopy Suite here.
We see it,
Looks
thank you.
good.
Perfect. All right, so I'm not sure how many of people present here today know how Gatan Microscopy Suite or digital micrograph looks like. But for those who do not know, I'll briefly go through the main features of the interface of the software. On the left, you can see microscope system diagram, which will basically tell you what's going on with your microscope, such as whether the beam valve is on or off, whether the beam blanker is on or off, what camera that you're using. Is it a K3, is it a Stella, OneView, Rio, or any other Gatan camera? If you're using an energy filter version of the camera, you will have the opportunity to either center the zero loss peak or do a full tuning of the GIF. It will also display whether you have calibrations done for the software suite that you're using, such as, in this case, Latitude D. You can track the camera quality, the monitoring of the camera, whether your camera is working okay or not. In this case, the light is amber, but usually in all the cases, you should see a green light. That means the camera is functioning as it's supposed to. And also you have a stage tracker, which lets you go to a particular position and recall that particular position as you are doing your data acquisition. On the right is a technique manager, which will essentially tell you how many techniques you have available depending on what kind of licenses that you have installed on your system. In the case of my computer, I see Latitude D, S, T, TFAS, all the flavors of Latitude essentially. But for the sake of this demo, I would be focusing on Latitude D. So once you click on Latitude D icon, you see a bunch of palettes popping out, and you will also see some of the calibrations which are relevant to the technique. Now I'll be hiding all the palettes that are not necessary for this demo, and I'll be focusing on the first palette that you'll be focusing on, and you'll be doing something the moment you start Latitude D software. Now, the first thing that you see here is that you have an opportunity to either create a new session, a new Latitude D or micro ED session. The second option is to create a new session based on a prior session. That means if you have set up a session maybe 1 year ago, half an hour ago, or half a year ago, you can take that session as a template and create a new session based on that session, which is very useful in many, many cases because you have set the magnification, the illumination conditions of the beam, and that way you essentially reduce your setup time to around 80%. And in some cases, you will need to continue a session, such as something happened because sometimes mishap happens with the software. You can continue the session that you started maybe half an hour ago. And also in some cases, you load a grid on your microscope and you stop collecting the data, and the next day you come, you would like to collect more data on the same grid. You can continue this session, and you can use the same montage that you created in the previous session and continue from there. Now, for the sake of this demo, I'll create a new session from scratch. So it will give you the opportunity to save the session, and it automatically defines the date and the timestamp, such as 2021, 12:09, 13:25. Since I'm on PST zone, Pacific time, so it's going to be 1:25 here. I will be selecting the default name of the folder, and now the session has been created. So the next few things that you will see as the palette options is the states, which in Latitude D, there are 4 states in total, named Atlas, Grid, Whole, and Data state. Where Atlas state is essentially a state which is in the low mag mode of the microscope, and it's set up such a way that the field of view that you have is a few grid squares of a grid. Now, grid is a state which is also in LM range or low mag range, and it is such that the field of view that you see on the camera is essentially 1 grid square. A whole state is essentially a survey state, and this is set up such a way that you will see a few holes of a quantified grid, or a few bigger holes in a lacy carbon grid, with a field of view essentially within 5 microns to 10 microns. And data state is a state where you'll be collecting your data. It will have 2 illumination modes. One is the imaging, and the second is the diffraction. And this is something which we'll go through in this demo. Then you have tomography setup, which will let you define what is the maximum and the minimum tilt angle that you'll be using for your data collection. System stability, which will let you define how many hours after which you'll be doing automatic dark references, beam centering, ZLP centering if you have a GIF. Fine alignment, which will click 5 images and let you align from low mag to the highest mag so that whatever feature that you see in the low mag is the same feature or crystal you see in the highest mag. And finally, Latitude Experiment. Now, for the sake of this demo, I will be setting up one of these 3 states because they're very similar, and the data state because it is a little bit more complicated because of the 2 illumination modes that it has. Now, to create an Atlas state, what you'll be doing is that you'll be clicking a gear right next to the Go To button, and it will open a dialog which is called Manage States dialog. And this state dialog gives you the opportunity to create a new state, copy a state, or rename or delete a state. In this case, since we are starting a session from scratch, I will be creating a new state. The moment you click New here, it will ask you to set the microscope conditions to the imaging mode, adjust all the parameters and the illumination conditions, and then click Next. So essentially, you'll be going on your microscope, you'll be adjusting the magnification that you need for that particular state, and then you'll be selecting the illumination conditions, the beam brightness, the spot size, the beam shift, the image shift, the projector shift, if you're using a Joule microscope. And once you're done with setting up all the microscope parameters for that particular state, you'll be clicking Next. So it's asking me to put the microscope to the imaging mode. And which I have done. And once I have done that, I can click Next. And the next thing it is asking me to do is to adjust the imaging parameters on the camera, such as in this particular state, you can define what will be the exposure time, what will be the frame rate, or the total number of frames that you'll be having in that particular state. If you would like to save a stack, you can do that. Or if you would like to correct the drift associated with beam-induced motion, you can do that as well. So in this case, I'll be using an exposure time of around 1 second and a total number of frames 10. And since this is a simulation, you would not be seeing much image information here. But once you have that image, you essentially click Next, and you can name the state. And in this case, I will be naming it as Atlas. And once you have done that, click Finish, and that state has been saved. And similarly, you'll be creating grid and whole states at different magnification. Again, usually Atlas and grid will be in the LM range or the low mag range, and the whole and the data will be a higher mag range. When you're using a Joule microscope, it will be mag 1 range, and if you're using an FEI microscope, it will be the SA range of the microscope. Next, I'll be essentially going through the data state because this state has multiple modes, and this is something what I wanted to cover in this demo. Now, since the data state has two modes, one is for imaging and the second one is for diffraction state. So when you click on the gear next to the Go To tab of the data state, you can save the data state first in the imaging mode. You click New, and it will, again, ask you to set the microscope parameters in the imaging mode. And once you have done that, you click Next. And now it will ask you to take an image, and we have already collected an image. I will click Next. And the next thing it will ask you to do is to move the microscope illumination state to the diffraction mode. And also in this case, you can insert the beam stop if you would like to insert it, if you're using a camera such as K3 or K2, which is beam sensitive. And once you have done that, you simply click Next. It will ask you to take an image. You will take an image, and you click Next. And then you can save the name of the state. And in this case, I'll be saving it as the data state. And once you're happy with it, you click Finish, and it will have it saved for you. Now, for the sake of ease of this demo, I have created a session for this demo in particular, where I have saved and created all these 4 states, and I'll be continuing that session. And this is one of the examples how continuing a session comes really handy in many, many cases because it saves a lot of time, especially when a mishap happens. Now, in this case, you will see that I had created a session before, which is called D_new, and it has all these 4 states set up already. And the reason and the way that you know that these states are already have been set up is when you see an asterisk next to the state. Since you see this star or an asterisk, that means that state is ready to be used for the experiment. Now, after all these states are set, you have the opportunity to define the minimum and the maximum angle you'll be doing or collecting your TIL series with. And in this case, I'll be selecting -60 to +60. And in some cases, you will be limited to plus or -30. And these are the things that will be dependent on the microscope stage and also the speed of the camera that you're using. It is imperative, since it's a continuous tomography or a continuous TIL series acquisition, the stage has to be of a good quality. That means the distance between the optical axes and the tilt axis should be minimum, and the distance between the mechanical and the optical eccentric position should also be as less as possible. And once you define the minimum and the maximum angle for your TIL series collection, you simply click Test Tilt Speed. So what this button would do is that it will tilt your CompuStage or your stage of your microscope from -60 to +60, and it will calculate the time it took for that 120-degree rotation. And once this calculates the time that it took for the full rotation, it will tell you it will need 6.09 seconds. And once you know how many seconds you need, you can simply click Next. And the next palette will let you define system stability parameters, such as after how many hours automatic beam centering will be done, after how many hours automatic VLP alignment of the GIF that currently I'm not using, but if I'm using, after how many hours it will be done. And if you would like to define after how many microns or micrometers you'll be doing your eccentric height tuning, you can also define that. You can make it more tolerant, or you can make it more narrow if you would feel. And if you click Next, you will have the opportunity to do fine alignment. So this step is, as I mentioned before, it will click 4 images for you: Atlas, Grid, Whole, and Data State. And it will let you make sure that whichever crystal or the feature that you're concentrating on in the low mag is well aligned with the highest mag possible, which is the data state. So that whatever crystal that you're targeting in the low mag is the same crystal that will be imaged and the diffraction tomography data will be collected on. When you go next, you have Latitude Experiment, and in this case, I have started this experiment with an atlas or a montage size of 1 by 1. That means 1 image by 1 image. Now you can increase the atlas size to 10 by 10 or 20 by 20, dependent on the magnification that you're using for the atlas state. And as you're increasing the size of this montage, you can also see how many microns of the grid that you're covering. As you increase the atlas size, such as 2 by 2 here, you will see that this amount of grid is being imaged or being covered in your montage. Now, as I mentioned before, this is the setup that I had created for this demo for today. What I'll be doing is I'll be simply removing everything and I'll be going from scratch. Now, this is a montage, which is 1 by 1 that I had created. And this is the grid square that I'm interested in imaging. So for the sake of this demo, I will delete this position so that I can walk you through it properly. Now, since this is a grid square, which I would like to target, because I see a few crystals there, which are very, very small. And also I see that the vitrification of the grid square for this one is nice enough, and I would like to proceed here. So simply what I'll be doing is that I'll be adding a position. So let's say this is the region that I am interested in imaging. I will be clicking on this hole, and I'll be clicking Schedule. And once you go to the Latitude Task Manager and you click Auto Navigate, you can see exactly what is happening at this stage. And you can see that it did eccentric height correction, did eccentric position, did refinement of the position, and then reference refinement. And then the next step for it to do is to schedule an acquisition of that whole image. Now, anything green you will see here means that it is scheduled for acquisition and it already has scheduled and it's in process. Anything yellow, that means is selected for acquisition, and anything blue, that means it has been acquired already. Now, since you see this whole image is already blue, has a border blue, that means it has already been acquired. Now, since this whole image has been acquired already, I will check and see what I would like to image. So let's see if this is a particle that you would like to image. Now you have two alternatives here. Either you can screen this particular position, or you can directly click a whole tail series, or collect a whole tail series at this particular position. So since I mentioned that you have an opportunity to see whether you would like to screen your crystals before collecting a full tail series, first I will be going through the screening process. So let's say I would like to add a screening position. So I make sure that it says add screening position, and I click on this particular area for screening, and I click schedule. Again, when you click auto navigate here, you can see exactly what's happening. So you saw that the stage is moved to this position, refinement of the position was conducted, followed by screening of this particular particle. And once it has screened, it will give you the result or the final data image in the diffraction mode, where you can see and assess the quality of the crystal. Now you see that it has already acquired a diffraction image. It shows you the diffraction quality, and you will see that a beam stop has already been inserted because this is how we set up the states. Now, dependent on how you see this diffraction image, you can see, okay, the crystal is twinned. I would not like to collect data on this crystal because I don't want a twin data set because it's hard to process. So in that case, you can move on and select another position. But let's say you would like to rescreen this same position. What you can do is that you can click on that screen tab, which will give you all the positions that have been screened so far. And you can change perhaps the tilt angle, because sometimes when you rotate the crystal, you get high resolution there. You get better diffraction spot separation there as well, which might help you assess the quality of the crystal. So that way you can rescreen the same position again using different parameters. such as the tilt angle or the exposure time. If the crystal is thicker, you might want to increase the exposure time. So this is how you can collect data or screen the data or crystals before you collect a full tilt series on it. Now, the second way of collecting data with Latitude D is that you can add a tomography position directly. Let's say in this case, I would like to add a tomography position for this particular particle, which is in the vitreous size. What I will do is that I will click Add Tomo Position, and I will select that particle. And once it's selected, as I mentioned before, anything selected will be yellow, anything scheduled for data collection will be green, and anything blue means it has been already acquired for that position. And once I'm happy with my selection, I click Schedule, and it's green. That means it's already in progress. And I will click Auto Navigate here to see what's happening. I see that it moved to this particular location. Position refinement for that crystal was done as well. And now it is collecting the tail series. And everything that is happening is also can be seen in the output window here, which will give you more information of the particular subtask that is in progress. Now I see that it has selected the positions, and I have the stage is being tilted continuously and the data is being acquired. And you see that 60 frames in total has been acquired for 120-degree rotation, and the data has been saved in DM4 format. And you see the projection image for this crystal, and I like the quality as well. And you have the opportunity to invert the contrast if you would like, which is something crystallographers would appreciate, where you can see the contrast inverted and you can see the quality as well. And if you would like to load the TIL series that you just acquired, you can click TIL series here. And it's loading the series. And then you have the opportunity to play the whole TIL series and make sure that you collected a good data set. Now, since the TIL series has been already loaded, I will switch on with the slice player and see the whole TIL series. And I hope you can see this diffraction TIL series here. And with this video, I would stop my demo, and I will be happy to answer any questions that you might have at this point.
Thank you very much, Sahil, for this beautiful demonstration of the Latitude D software. So I'm looking and I don't see currently any questions in the Q&A, so please keep putting them in and Sahil will answer them at a later time. But I actually have a question for you. So you can collect multiple ROIs, and I already saw that the eccentric height can be automatically adjusted. But is there also an optical adjustment that the software can do at every ROI that you want to acquire a tomography tilt series?
Absolutely, it's a very good question. Yes, you can do optimum or the optical eccentric position tuning as well as the mechanical one. So usually when you're tilting your stage and collecting diffraction data, mechanical eccentric position should be there. So in that case, whenever you're about to collect a TIL series, it will go to the eccentric position, the mechanical eccentric position. But if you would, for some reason, would like to only do the optical one, you have the option for doing that as well.
Thank you very much. So thanks, Sahil. So we'll continue now our program with another student speaker, and we'll continue with Stephanie Ribet. She's a PhD student in the Material Science and Engineering Department at Northwestern University, worked with Professor Vinayak Dravid, and she will talk to us about a very interesting combination of teeth and scanning electron diffraction. So please, Stephanie, take it away.
Well, thank you very much, Paul. It is my pleasure to be here with all of you today to talk a little bit about the work we've been doing to understand the nanoscale building blocks of human enamel. So I'll start by talking a little bit. So human enamel is in a category of materials that are biominerals. And animals create biominerals for all kinds of reasons, including for structure, for stability, for protection. And our favorite example around here is, of course, beaver teeth. Beaver teeth are remarkable materials. They can take down trees with these biominerals. Of course, we're very interested in human enamel as well, human teeth as well. And one particular part of human teeth that's of interest is the enamel region. This is the upper top coating of the tooth. This is a very high hardness and stiffness biomineral, and it is used to protect against abrasion. You're doing thousands of cycles of chewing per day. Like many other biominerals, enamel is a composite material with a hard and soft component and features at multiple length scales. So you need really specialized characterization to be able to understand this material. But doing so is important because it has, these biominerals have unique forms because of their unique functions. Being able to do so, you can understand not only the forms of the materials, but also the biological processes that contributed to their formation, and also inspires the development of new synthetic materials. The structure or the existing model of enamel is, as I mentioned, hierarchical. So on the micro scale, you have these rod features. Looking then at higher resolution, you can see that there are nanoscale features. These are grains. And then we can look at each grain individually. And we can see here, there's an intergranular region here, and these are the grains. They are largely coherent, and they're made up of, then we can go at higher resolution to see that they are made of hydroxyapatite, and we can see the individual atoms. We also, from atom probe data, have been able to map some chemical features within these materials. So you can see there are small substitutions. Again, this is the intergranular region here. This is sort of the model as it exists of what human enamel is. Despite all the amazing work that already exists, there are still some questions about the orientation and strain within these materials, and we're going to be using STEM to be able to probe what's going on. So I'll explain a little bit more about our methods. This is a transverse cross-section of a human tooth, and again, you can see the enamel here. This is what we were looking at previously. This is the rods on the microscale. And then these white arrows are going to indicate the orientation of the crystallite that we saw previously, So what we're going to do is we're going to take fib cross sections. So one is going to be this way, where we're going perpendicular to the orientation of the tooth. And then one is this way, which is going to be along the direction of the grain. And we're going to study these materials with STEM. As our previous speakers have talked about, STEM is a really powerful technique for being able to probe these materials. And the reason for this is STEM has a very small probe size. You can get multimodal information, and also you can cover a large field of view. So we're going to be using STEM to look at these fib cross sections. We're going to be using two STEM techniques. The first is going to be more conventional dark field imaging. And this is like the images we saw in the previous slide. In order to be able to get these images, we're going to need to use cryogenic temperatures to minimize damage, but we can do really high resolution imaging. The other technique we're going to be using is 4D STEM. And this is a low dose technique. We're going to collect the entire diffraction pattern. And as Roberto explained before, because diffraction space contains such rich chemical and physical information, even with the sparse low dose data set that we use to avoid damaging the sample, we can reconstruct interesting information about our specimen. So using these two approaches, I'm going to tell three very small stories or things that we've learned about enamel through our work, mostly with 4D STEM. So first, I'm going to be talking about grain distribution and the distribution of grains in these specimens. Then I'll be looking at higher magnification to be looking at strain within one single grain. And then lastly, we're going to look at the intergranular structure, the intergranular region, areas between grains, to understand how these two pieces fit together. So starting first with one low magnification area where we're looking at grain distribution. Again, as explained before, we're going perpendicular to the orientation of the grains. So we're looking down the z-axis, and this is the diffraction pattern averaged over the whole specimen. You can see this 110 family of planes reflected here, which again indicates our orientation. Because this is a 4D STEM data set, we can go from reciprocal space to real space. So first thing we're going to do is integrate the Brightfield region, and we end up with an image that looks like this. And we can start to see the features in the specimen now. We can see some grains and some other contrasts, but we don't necessarily understand its origin. A dark field image is very helpful as well. So we can do a virtual dark field detector and we end up with an image that looks like this. And now we can see more clearly where the different grains are. But again, we don't have any quantitative information about where the grains are or how they are oriented. One approach that people can use is to do other kinds of virtual detectors. So here we're going to use quadrant detectors. So we're going to do X and then Y, and you can subtract opposite quadrant detectors. So this will tell you about the deflection of the beam and also the tilt of your specimen. And you can see much more interesting features in these images as compared to the dark field image before. And you're going to see a mix of strain and orientation contrast that is contributing to the, or mix of strain and orientation that's contributing to the contrast here. But again, this doesn't necessarily tell us any quantitative information about the orientation of grains. And to be able to do that, we're going to use our own method that we've developed to be able to look at the rotation of grains. So in order to explain the method, let me go back to looking at the structure of this material. Again, it's hydroxyapatite. And if you project this material down its C axis, it has six-fold symmetry and a reflection pattern that looks something like this. What we're going to do is create a virtual detector, a very thin ring that matches exactly the reciprocal length of these reflections right here. And we're going to go around and collect the intensity at each position around this ring. We can unwrap this ring and then we can plot this here. And again, you see very nicely the six-fold symmetry, all the green peaks. And then we're going to find the area of maximum intensity. And then again, we're going to divide by 6 to account for the symmetry and plot that for each position in real space. So then we can show relative grain orientation within the region. The other thing we're going to do with this annular detector is we're going to integrate it, because places where we are most on axis and most well aligned, we're going to have more intensity within this ring. And we end up with a map that looks like this. So you can see some grains are very well aligned along the C-axis, and there are areas that are less well aligned. So we're going to make these areas less intense in our final orientation map. Combining these two pieces of information, so our relative orientation and also our intensity, we can end up with a map that looks like this. And this is a map of orientation within our sample. And you can see here all the different grains now nicely highlighted. If we want to make this more quantitative, what we can do is look at the difference in angle between nearest neighbor pixels. So if this is our pixel of interest, we'll look at the 4 pixels closest to it. We would expect most of these values to be 0, because as we can see here, these grains are largely coherent. But then we can see values that are non-zero and understand the grain boundaries within this area. So we can see here, as expected, that most of our nearest neighbors are 0, but then we can see over here that we have a lot of low angle grain boundaries, which is what's expected from the literature from experiments with other different types of characterization techniques. So in summary, we've used a 40-stem approach to be able to map the orientation of grains within the specimen. So now we're going to look at one specific grain. And we can see here, this is a different specimen, and we're doing a virtual Brightfield image as before. And you can see we have one grain here with strain contrast. Our dark field image actually reveals that this is in fact one larger grain, and this is the core right here, and this is the intergranular region around it. We can confirm this with diffraction, taking a diffraction pattern from both the red and the yellow region. We can see these diffraction patterns are mostly oriented, their orientation is nearly identical. And then if we look at areas outside this grain, we see a little bit of tilt away from the C-axis, and this is something that will be important that we're going to try and probe, and I'll talk about that next. So before we do that, the first thing we're going to do is, as before, probe the orientation within the plane of the sample, and we end up with a map that looks like this. Again, this is the core of the grain. We set this at 0. And around the core, you see some rotation away. And then especially at the intergranular region, you see more rotation around your crystal. We're also interested, though, in understanding the deflection of the beam, the out of plane tilt. And to do that, we're going to use another method. So I'll explain here again. So this is one diffraction pattern here. We're going to create virtual detectors, 6 of them, like this. And within each detector, we're going to find a place of maximum intensity. So we have these 6 candidate dots. We find the one that is the most intense overall, which is dark blue. And then we look at its opposing one, the yellow, and we find the difference from the dark blue to the center and the yellow to the center and find their difference. The difference between those two distances is going to tell you something about beam deflection, or your out of plane rotation. And we end up with a map that looks like this. It's interesting to see this map because we see some deflection of the beam near the core of the grain, and then also in areas in the Brightfield where we saw strain contrast before, and now we can see some deflection of the beam out of the plane as well. So combining these two pieces of information, in plane rotation and out of plane rotation, we can start to understand strain with a basic rigid rotation model, especially because there's a direct link between orientation and strain and stress. So we're going to use a basic model like this and input our two angles here. We don't need a third because it's relative strain. And combining this information, we end up with strain maps that look like this. So again, around the core of the grain, we have some strain and some strain out here. And then we get some out of plane strain information as well, which correlates with where the beam is deflected. To compare, we can measure strain in cryostem images. This is only going to give you in-plane deflect strain. And what you do is you take high resolution images, and then you do automatic detection of the atoms, and you look for subtle displacement, and you use this to map strain. And you can compare our strain, which we did with 40 STEM with much lower dose without the need for atomic resolution, and the cryostem, and you can see there's similar features in both. So for example, strain accumulating around the core region. And so it's interesting to compare these. They give similar qualitative results about the strain within one grain. We're also interested in learning about the intergranular structure. Now that we've learned about these grains and that they're largely coherent but do have strains. So how is the strain, what's happening at the intergranular region? In our cryostem images, we see some darker regions here, which looks like it could be, we're not quite sure exactly what it is. So we wanted to understand that, and we can do that with 4D STEM. So, and before I previously talked about how we're going to take a fib section perpendicular to the c-axis. So now we're changing orientations. We're going to go along these nanocrystalline building blocks. And this is the region where we're going to study. We can take a scanning diffraction or 4D STEM data set from this area right here, and we can look along between grains. So as we cross a grain boundary right here, you can see these are strong Bragg spots that are from this orientation of the crystal. And down here as well, you see Bragg spots at a different crystal. In between, you lose the strong Bragg intensity and you see a little bit more brightness towards the central beam. So this is telling us that we're losing our strong crystalline order. So we have some disorder or some amorphous region going on there. We can do the same thing at the next crystalline domain, and we see the same effect where at the central spot, you are losing your strong Bragg disks. This tells us a little bit about the disorder that we see at the intergranular region in the enamel. So in summary, we've looked at the grain distribution at lower magnification of enamel. Then we've looked at the structure of a single grain. And then finally, we've studied the region in between grains. Going forward, there's more work to be done. We're interested in connecting this new structural information to the earlier maps I showed of chemical distribution within the sample. There's also ways to add more autonomous processing into this workflow. And also we're working on applying this to other systems. So I'd like to thank my advisor, Professor Dravid, for his help with this, and of course, Roberto, who's been really helpful with all the STEM, and Professor Yoster as well for his help on advising related to enamel, and our collaborators at Cornell, and then of course, Paul, who's been a great collaborator on this project. So I'd be happy to take any questions.
Thank you so much, Stephanie, for sharing your work. That is really something to smile about, no pun intended. I am looking at the Q&A, and I have one question for you here. It's from Mahmoud. He said in slide 12, do you consider this layered nanocomposites interface as a grain boundary? So if you can go back to slide 12.
So I think what you're asking about are these layers. These are going to be your basically your grains. So these would in between would be the intergranular region. And Paul, you can correct me. This would be like a grain boundary, correct?
Correct. Those are grain boundaries. Mm-hmm.
Just want to make sure I'm using the right term. But these are the coherent grains that we saw before, just the other orientation.
Okay. So in lieu of time, let's continue. So please keep asking questions in the Q&A session, and Stephanie will try to answer them. So we're going to continue now with another PhD student, Carolin Wahl, who works also in the Material Science and Engineering Department at Northwestern University and is co-advised by Professor Vinayak Dravid and Professor Chad Merkin. And she will talk to us today about scanning electron diffraction for precision mapping of structures and interfaces in heterostructured nanoparticles. So with that introduction, Carolin, please take it away.
Thank you, Paul, for the introduction. I hope you can all hear me. I'll share my screen.
We can see it. Thank you.
Thank you. Okay, yeah. Like Paul was saying, I'll talk a little about how we can really take the 4D STEM platform, and I'm going to push it down to the resolution limits and go look at what we can do on the single nanoparticle level. So in the Merkin group specifically, we really specialize in the synthesis of complex nanoparticle structures. And we want to know, well, what's going on in these more complicated systems. So as an overview, the way we make these nanomaterials that we're studying is using a technique that's called scanning probe block copolymer lithography, or SPBCL. And the way it works is basically we make an ink that contains the metal precursors that we're interested in having in the particle, and the block copolymer inside in water. And then we use a scanning probe tip, just like an AFM, to deposit the really small volumes that we call nanoreactors on predefined locations on a substrate. And so this is what they look like in an optical microscope image after we pattern them. So you can pattern them in regular arrays, for example. And so we can make these arrays of nanoreactors. And then we can anneal them at elevated temperatures, and that causes all of the precursors that we put in the ink to coarsen together and form a single nanoparticle in each nanoreactor. And so in the past couple of years in our group, we have made a number of different materials that way, going from just like simple elemental nanoparticles to more complex structures like alloys, intermetallics. But perhaps most interestingly, we can make these heterostructured nanoparticles that contain more than one phase. Because the advantage of having a nanoreactor is that the spatial confinement that those precursors are in forces them to go and coalesce into a single particle, even though they aren't miscible really. So we can get particles that contain one or more interfaces between different structures. So that makes them intrinsically interesting for us to study, because we have single nanoparticle with immiscible phases that can have all kinds of orientations and interfacial structures in there that might have a number of interesting properties that we might be seeing there. So we're really interested in figuring out what are the crystal structures and orientations, and what do those interfacial regions look like inside of those complex particles. So the perhaps simplest way of looking at crystal structure on the nanoscale is using FFT, of atomic resolution images. And so I'll show an example here. This is a fairly simple gold, silver, copper model system. So when you take an image of that, what you get is you get a region that's gold, silver, and you get a region that's gold, copper, because silver and copper don't mix. So gold, silver, it forms a homogeneous FCC alloy. And then gold copper can form 3 different intermetallic structures depending on the ratio of gold to copper. In this case, it's the gold copper 3. And so we get a nanoparticle that has this interface going on over here that is very obvious between like the 2 regions. And so, but already if you look at the FFT of this whole particle, this is a mess. And even if you filter it, you get rid of some of the streaks, but this is going to be really hard to look at and see what's going on. So we can zoom in to certain regions of that particle. So we can look at the center region right here. And so we can see here is again the phase boundary. So this part is going to be the gold copper region, and this part is going to be the silver copper region. There's a number of things going on that you'll notice. There's something that looks like a grain boundary, something that looks more like stacking faults. There's some twinning going on here. And then we have the interface to the gold copper. And so we can take FFTs of different regions of this to work out what the crystallography looks like here. So when we do that, we'll see over here this part is what's going to be the gold copper 3 intermetallic. Still kind of messy, but it's a single crystal, so this is something that we can index in theory. And then we can look at some of these larger regions over here, and we can see the green and this orange one over here. They're the same thing. So what we have in between here is probably like a stacking fault or something. Turns out if you zoom in, that's exactly what it is. And then over here, we have a grain boundary of some kind. So we have a different orientation between this grain over here and this grain over here. So there is a lot we can learn from doing this FFT image analysis, but we are also running into limitations here pretty quickly because we don't have a lot of pixels to work with. If you're taking atomic resolution images, the largest you can do reasonably is like a 1024 by 1024, or at the most a 248 by 248 pixel image because of how much your sample is drifting. And so if you imagine like taking small regions of this, you're working with really, really small pixel sizes. So you can see how noisy those FFTs become. And so I really don't have an option in an image like this to look at a really small region like this part over here. I'll have so few pixels that I won't be able to see much. And so what we can do instead is, like we've alluded to before, is we can turn to 4D STEM to try to get the full diffraction pattern at each pixel rather than having to live with the FFTs here. So Roberto did a great introduction of how 4D STEM works. So what we're going to be doing is we're going to take our electron beam, we're going to raster it across our sample. And then instead of just collecting the bright and dark field images like we did before, is we're going to be collecting the full diffraction pattern at each of the pixels. And there's a number of things that we can learn from that. What we're interested in specifically in our systems is we want to map out the orientations of the crystals that are there, like Stephanie showed us really beautifully previously. We also are going to be interested in the phases that are in there because, like I said, we're going to have more than one phase in the particle and potentially a whole lot of them that we don't know ahead of time. And we're also ultimately going to be interested in working out what the strains are there, especially near the interfaces. There's going to be really interesting electronic structures that come out of having strained crystals near interfaces. And so when we do that, I'll show first a pretty simple model system that's just silver copper. So we'll have two FCC phases that are emissible. And so here is an example of, here's like the dark field image of that particular particle. And then we took a 4D STEM data set from this. And then we can take all of the diffraction patterns, image them together. This is what the full diffraction pattern basically looks like. There's not much you can see here. So we'll select different areas of interest here. And so what we can do is, like we've seen previously, instead of having a fixed detectors of shapes that are defined by whatever our microscope is, we can put our detectors anywhere we want. So if we take a virtual detector, place it around the center disk, like here, then this is like having a virtual Brightfield detector. And what that gives you is a virtual Brightfield image, like that. And then we can do the same thing in the dark field region. And in this case, instead of having a single annular detector or a few annular detectors, we can place our detectors around diffraction disks that correspond to a particular grain. So if one example of this is like if I pick these three spots over here, they're barely visible in the average, but those correspond to this grain over here, which seems to be very close to like a 100 type zone axis. So you can get this grain just highlighted selectively because these diffraction spots correspond only to this orientation. And then we can select another set of spots, and that gives us this larger grain over here. And then what becomes really interesting in this multiphasic particle is if we look at this last one over here, you can see this grain has the same orientation as the one in green, but it has a different lattice parameter. You can very clearly see the change in spacing here. So this is where our phase boundary is. Between this part over here and this part over here, this is where we transition from silver to copper. So the blue part over here with the larger spacing, that's where the copper is. And then the rest of this is going to be silver. So this is really helpful for us to work out what exactly those interfaces are and where they're located in space. So the next thing we can do with this is look at a slightly more complex case instead of putting just two metals in there. Here is a gold, copper, cobalt, nickel particle. What you would expect to see from this is also a biphasic particle. One is going to be gold, copper. The other one is cobalt, nickel. Cobalt, nickel, again, forms an FCC solid solution. And this one is going to be some intermetallic. Again, here we have the particle. Here we have the diffraction pattern. And we look at the virtual bright field image, which doesn't tell us all that much, except there's probably a lot of diffraction going on in here, rather instead of the outside part over here. And then we can, again, look at dark field images of a couple of grains that we can find. One of them is this one right here, looks like about where the phase boundary seems to be, given this the dark field image that we have. So we selected those 4 spots over here. And then very close to this, you can see like those spots are kind of elongated. So very close to this, we actually have a different set of spots here, which again, kind of similar orientation, different lattice parameter. So this is where our other phases, and you can see all the spots that are kind of in between, the bright ones. So this is likely the intermetallic phase because it has more spots. So in this case, we have to make our virtual detectors really small because those lattice parameters between the gold, copper, and the cobalt, nickel phases are actually really close together. So there's a lot of overlap between the disks that we're seeing. But we can still, if we make the detector small enough and use enough spots so we can integrate for enough intensity, we can still visualize those grains the way we need it to. And then lastly, we find there's some region over here that's still missing that turns out to be a grain that's like fairly far away from any reasonable orientation. We can still find and highlight it though. So yeah, this is really something that gives us diffraction on the nanoscale to an extent that other techniques really can. And so we're really interested in what else we can learn from all of the structures that we can make. Because in order to do this really well, we need really fast cameras, we need really high spatial resolution. So we're like uniquely equipped now to be able to study systems like this. And more importantly, in the future, we'll be able to take this kind of data, look at unknown materials. And I'll leave you with a little bit of an outlook here, which is we can incorporate the 4D STEM diffraction measurement into other detector techniques. We can have a 4D STEM experiment running at the same time as we get a dark field image and we get EDS, and all at the same time. And we can use that to simultaneously acquire a whole bunch of signals from a single nanoparticle, work out what the elemental compositions are and their distributions, match that to the crystal structures, and work out really what a whole number of new materials that we might find in our syntheses might have in store for us. So with that, I'd like to thank my advisors, Professor Merkin and Professor Javid, all the office staff and the groups that I'm a part of that help us make these things possible, my mentors and collaborators, the staff at NUANCE, in particular, Roberto and Xiaobing, who've helped me a lot, like doing these experiments, and all the subgroups and group members that I get to work with every day. And with that, I'll be happy to take any questions.
Thank you very much, Carolin, for this wonderful talk. So I see one question in the chat for you. So first is more of a comment: wonderful insights to multi-component materials, precise characterization. And the question is, in the gold, copper, cobalt, nickel compound, how accurate is using the lattice parameter to determine unary or binary phases?
There are limits to how accurate this is. So eventually, especially the biggest issue perhaps is that the nature of the interface is not necessarily entirely clear. If you have a whole lot of elements in there, that interface is not going to be sharp. It's going to be washing out. So you have like you can kind of see it here, right? There's like a broader region of an interface versus this like really, really sharp version over here. And so that's gonna make it hard to distinguish what's what. So in the long term, if you go to really complicated systems, you're gonna want additional techniques to do that. So for example, we would add EDS to this, right? While we collect the 4D STEM data, we're gonna have an EDS map running and we're gonna work out, okay, then we have cobalt nickel on one side, and we have gold copper on the other side. And those relative ratios are going to give us an idea of what that lattice parameter is supposed to be, right? In a FCC alloy, the lattice parameter is going to depend on the relative composition of the alloy. And so that's going to help us get to the precision that we need to be at. Great question.
Thank you for the question. And Carolin, thank you so much for the wonderful talk. So we're at 4:16, so at the end of this session. And so with that, I'd like to give the word back to Tirzah and Roberto for some closing remarks.
Thank you, Paul. And thank you everybody for hanging on with us all day. I know it was a long day with a lot of different types of information. These talks will be recorded so you can watch them later. And so if you missed any and you just caught this afternoon and you missed some of the morning ones, they will be available. And of course, thank you to all of our amazing speakers. Thank you for making the time to be here and sharing with us all of your insights into these techniques and sharing some of your research. So Roberto, do you have anything you'd like to say before we sign off?
Yes, just I'd like to thank again all the speakers and who help us to organize. And one quick remark is that just keep in touch, right? So visit like NUANCE website and ask questions. So we are here to help and then find the best way to solve your problems.
And of course, thank you to, like you said, all of the organizers. There are a lot of people here at NUANCE on the back end that did a lot of the legwork. So thank you, Katie and Marie and everybody else.